friends, welcome to our channel ECE Tricks. In this video, we are going to discuss the next set of topics in lecture number 2 of Electron Devices series. So we are going to discuss these topics in order: mass action law, conductivity of semiconductors, both types, so intrinsic and extrinsic, and Fermi-Dirac function, and what do you mean by Fermi energy level for both types of conductors, either intrinsic and or extrinsic. Both we are going to discuss, and we are going to deal with a lot of formula in this video. Particularly a lot of energy level diagrams have also been included. Okay, so some constants also have been discussed in this video. It will be definitely useful for you. Watch this video till the end for better understanding. So this video is mainly useful for your semester exams, TRB exams, or other technical exams like GATE, TNPSC, and so on. Okay, so come, let's start the video. If you haven't subscribed to our channel yet, do click the subscribe button and press the bell icon also for further updates. Come, let's start the video. So first we are going to discuss about mass action law. This is a very important law in semiconductors. Okay, so this law states that in a semiconductor under thermal equilibrium, the product of the free negative and positive charge concentrations is a constant, which means this N refers to the number of electrons. Okay, it's the number of electron concentration. Okay, so electron concentration, and P refers to the whole concentration. The product of these two is equal to a constant. That constant is called as intrinsic carrier concentration. Okay, that constant is called as intrinsic carrier concentration. Intrinsic carrier concentration. Okay, referred to as Ni. Okay. Okay, so this is the mass action law. So the main law formula is this: N into P equal to Ni square. Okay, so N refers to the electron concentration and P refers to hole concentration. The product of the two is equal to Ni square, which is obviously a constant because Ni is a constant. Okay, so coming to N-type semiconductors. So we discussed in the last video, right? So N-type semiconductor, the majority charge carriers are holes, right? So the number of pentavalent impurities added will be equal to the number of electrons formed, right? Correct? So that point is very important. To keep that point in mind. Okay, so for N-type semiconductor, electrons are the majority charge carriers. Okay, so this same mass action law can be rewritten like this: Pn equal to Ni square. The N at the bottom indicates it is an N-type semiconductor. That's it. Okay, so N and Pn equal to Ni square. Okay, so in N-type semiconductor, the electrons are the majority charge carriers, right? So we can rewrite this NNS. Okay, so we can rewrite this NNS Nd. What is Nd actually? Number of donor atoms. That is, we are adding some pentavalent impurity atoms. No. So you remember that concept, okay? In N-type semiconductor, we are adding some pentavalent impurities of group 5 in the periodic table. I discussed in the previous video, right? So the number of donor atoms added will be definitely equal to the number of electrons, free electrons formed, right? So we can rewrite this Nn as Nd, correct? And Nd into Pn equal to Ni square. So from this we can calculate the number of holes in a N-type semiconductor as Ni square by Nd. Okay, so this formula is widely used for many problems, many calculations. Okay, similarly for P-type semiconductor, the majority charge carriers are holes, right? The majority charge carriers or holes I discussed in the previous video. So the same mass action law can be rewritten as P in the bottom, right? So because it is a P-type semiconductor, so we can rewrite as Np Pp equal to Ni square. Here, since in a P-type semiconductor, holes are the majority charge carriers, we can write Pp, that is number of holes in a P-type semiconductor, will be definitely equal to Na. What is Na here? Na refers to the number of acceptor atoms. Na refers to the number of acceptor atoms, because in P-type semiconductor, we will add trivalent impurity atoms. Trivalent impurity atoms are nothing but group 3 elements of the periodic table, right? So they are called as acceptor atoms because they create holes. Okay, so if one trivalent impurity is added to a silicon semiconductor crystal or a germanium, any semiconductor crystal, it will create one hole, right? So number of acceptor atoms or the number of trivalent atoms added will be equal to the number of holes, obviously, right? So we can rewrite this Pp as Na. Okay, so in the same way, here also we have written Nn as Nd, no? So same way we can write the number of holes equal to the number of acceptor atoms Na. Okay, so this entire equation can be rewritten as like this. Okay, Np into capital Na equal to Na square. So the number of electrons in a p-type semiconductor. This is the minority charge carriers, right? Since it is a p-type semiconductor, electrons are the minority charge carriers, correct? So this minority charge carriers can be calculated like this. Np equal to Na square by Na. So these are the two important formulae. Okay, so we are deriving this using mass action law. Coming to semiconductors, conductivity. Okay, so coming to semiconductors, we have two types of charge carriers, right? Electrons and holes. Even though one is majority and another one is minority, that's not a problem anyway. Both the charge carriers contribute to conduction, right? So semiconductors conductivity, we have to consider both electrons and holes in mind. Okay, so electron current density, first we have to calculate the current density, and using current density we can derive the conductivity. Okay, we can discuss that. First, electron current density. Okay, so electrons current density, the formula, please note the formula, N into E into mu N into E. Okay, here what is N? N refers to the electron concentration. As I said in the previous slide, N refers to the electron concentration. Okay, and here P refers to the whole concentration. P refers to the whole concentration, and E refers to magnitude of charge of electron or hole, anything. Okay, so E refers to magnitude. Okay, E refers to magnitude of charge of electron or hole, any charge carrier. Okay, this is a standard value actually, 1.602 into 10 power minus 19 coulomb. Okay, so this you might be learning, you might have learned already. Okay, then mu n and mu p. Mu refers to mobility. Okay, mu refers to mobility. So mu n means mobility of electrons and mu p means mobility of holes. Okay, so mu refers to mobility. Okay, then E refers to the electric field applied. E refers to the electric field applied. E refers to electric field applied. Okay, so this is the electron current density and hole current density. In electron, we are including the electron concentration N, and in hole current density, we are including the hole concentration P. Others, mobility also we have changed, right? There mu N, here mu P. That's it. Okay. Now, next we are going to calculate the total current density J. Okay, the total current density J. So, the total current density is contributed by both electrons and holes, right? So, the total current density J equal to Ne mu Ne plus Pe mu P. We are going to add both. Okay, so here the small e and capital E are common for both, right? So, we are taking E outside and we are putting the remaining terms inside the bracket. So here n mu n plus mu p, correct? So this entire term, that is with small e into n mu n plus p mu p, is referred to as sigma. Sigma is nothing but conductivity of a semiconductor. So this formula is very important. So this formula is very important, sigma. Okay, sigma is nothing but conductivity. Sigma is nothing but conductivity. Okay, so learn this formula, keep a note on it. E into n mu n plus p mu p. This formula is widely used for problems. Okay, so நிறைய TRB எக்ஸாம்ஸ்ல இந்த ஃபார்முலா பேஸ் பண்ணி ப்ராப்ளம்ஸ் நான் பார்த்துருந்தேன். அதனால கண்டிப்பா இந்த ஃபார்முலா நோட் பண்ணி வச்சுக்கோங்க. ஓகேவா, ஈங்கிறது 1.602 10 power minus 19, அதை நீங்க யூஸ் பண்ணிப்பீங்க. அதே மாதிரி என்னங்கிறது கொடுத்துருப்பாங்க, பிங்கிறதும் கொடுத்துருப்பாங்க. ஓகேவா, மியூ என் மியூ பி அதுவும் கொடுத்துருப்பாங்க. எல்லாத்தையும் சேர்த்து சப்ஸ்டியூட் பண்ணி கனெக்டிவிட்டி கண்டுபிடிக்கிற மாதிரி இருக்கும். ஓகேவா, this is the standard formula for any type of semiconductor. Okay, in case of intrinsic semiconductor, as I said in the previous video, for an intrinsic semiconductor the number of electrons and holes will be equal. Correct? That is equal to the intrinsic carrier concentration Ni. இது ஞாபகத்துல வச்சுக்கோங்க, n equal to p equal to Ni for an intrinsic semiconductor. Okay, so இந்த Ni க்கு வேல்யூ என்னங்கறத நீங்க கமெண்ட்ல சொல்லுங்க. ஓகேங்களா, நீங்க கண்டிப்பா படிச்சிருப்பீங்க, ஞாபகம் இருக்கு அப்படின்னா கண்டிப்பா கமெண்ட்ல சொல்லுங்க. Ni intrinsic carrier concentration ஓட வேல்யூ. Okay, so in this formula, that is in this conductivity formula, we are going to substitute n and p as Ni. Okay, since n and p are equal for an intrinsic semiconductor, that is equal to Ni. Okay, so n is replaced by Ni and p is also replaced by Ni. So now this Ni is common, so we are taking this Ni out. So E into Ni into bracket kulla mu n plus mu p. Okay, so this is the conductivity. This is the conductivity of an intrinsic semiconductor. Got the point? This is the conductivity of an intrinsic semiconductor. Okay. Okay. Next topic, Fermi-Dirac function. Okay, this is also an important topic in exams. So under thermal equilibrium, the probability of the energy level E being filled is called Fermi-Dirac function. Okay, in simple terms, we are considering a particular energy level. Okay, so that energy level is probability. The probability of that energy level being filled is called as Fermi-Dirac function. So either it can be filled completely or it can't be filled completely, right? So if it can be filled completely, for sure it will be filled means the probability will be 1. It will not be filled definitely, then the probability will be 0. That is, the Fermi-Dirac function will be 0. Okay, sometimes we can also say that in some situations there may be a dilemma, that is it will be filled 50% or it cannot be filled 50%. So in that times the Fermi-Dirac function will be 1 by 2, that is 0.5. Okay, so since the probability always lies between 0 to 1, okay, so if the probability is 0.5 or 1 by 2 means either it can be filled 50% or it cannot be filled 50%. Okay, 50-50. Okay, so coming to this formula, this very important formula, Fermi-Dirac function f of E equal to, this is nothing but a probability. We will be referring as P of A or P of E in probability, no? So the same kind of meaning only, this f of E. Okay, so f of E equal to 1 by 1 plus e power E minus EF by KT. Okay, so this is the formula. Please take a note on it. Okay, so this E is referred to that particular energy level. Okay, we are considering an energy level now. So that energy level is referred to as E, and EF is the Fermi energy level. EF is the Fermi energy level, and K is nothing but Boltzmann constant. T is the absolute temperature. Okay, in Kelvin. Okay, what is Boltzmann constant actually? Constant is nothing but it has to be contain a value, right? So Boltzmann constant value is 1.38 into 10 power minus 23 joule per Kelvin. It's an important constant in semiconductors industry mainly. So kindly take a note on it. Okay, this is a Boltzmann constant. Okay, Boltzmann constant. Okay, is nothing but Boltzmann constant. Boltzmann constant. 1.38 into 10 power minus 23 joule per Kelvin. Okay, and EF is the Fermi energy level. Okay, what is Fermi energy level? So in this Fermi energy level only we are going to discuss in the next slides. Fermi energy level varies for intrinsic semiconductor and for p-type and n-type also. Okay, so we can see that in energy level diagrams. But what is Fermi level? Fermi energy level means Fermi energy level is an energy level at which the Fermi-Dirac function f of E is half, 1 by 2. Okay, so as I said earlier, what is the meaning of 1 by 2 means it either can be filled or can't be filled, 50-50. Okay, so that probability, if that energy level has the probability of 1 by 2 for getting filled by electrons, then that energy level is called Fermi energy level. Okay, got the point? Then when this f of E will be 1 by 2, this term has to be 1, right? Then only this denominator will be 1 plus 1, 2. Then when this term will be 1, e power 0 will be obviously 1. So this numerator term, that is that e power, that power term has to be 0. Then only e power 0 will be 1, 1 plus 1 will be 2. Then when this power term will be 0, this e and ef has to be equal. Okay, so you got the point. So e and EF when gets equal, E minus EF, then it will be 0, no? So E power 0, it will be 1, 1 plus 1, 1 by 2. Okay, so that energy level is called as Fermi energy level. Okay, so both the definitions are very important, including this formula. Okay, and learn this constant value also. And coming to two cases, okay, so related to the Fermi-Dirac function. Okay, at temperature of 0 degree Kelvin, if this energy level, we are considering one energy level now, that energy level is greater than the Fermi energy level means, then the probability will be 0. We can check here E equal to EF, right? So when E equal to EF, okay, then temperature is also 0. We are mentioning the temperature also. So keep that point in mind, okay? So temperature, denominator term is obviously 0, and when this E is greater than EF, not equal, if it is equal means then the probability will be 1 by 2, right? If this E is greater than EF means this numerator term, that is this power term will be positive, right? So any number, that is any positive number by 0, that is any number by 0 will be infinity. So this number, this term will be infinity, right? So 1 by 1 plus e power infinity, correct? Okay, so 1 by e power infinity is infinity, right? So 1 by 1 plus infinity, correct? 1 by 1 plus infinity. Okay, so 1 plus infinity is nothing but infinity. So 1 by infinity is obviously 0. Okay, so this probability or this Fermi-Dirac function will be 0 when the energy level is above the Fermi energy level. Okay, so the temperature is same for both cases. So we have to keep in mind this condition only. If the energy level is greater than Fermi energy level, this probability will be 0. Okay, which means there will be no filled energy level above the Fermi energy level, right? Because the probability is 0. Probability 0 means there will be no energy levels, right? Okay, there will be no chance. That's the meaning of the 0 probability, correct? So there will be no filled energy levels above EF also. Second case, coming to the second case, at the same temperature of 0 degree Kelvin, if the energy level is less than Fermi energy level, that is if E is less than EF, what happens to this equation? See, if E is less than EF means this term will be negative, correct? So 1 by 1 plus e power, this term will be negative. Okay, so negative, that is any number. Okay, that's not a problem, but it will be negative by this temperature is 0, correct? So 1 by 1 plus e power, any number by 0 is infinity. Coming to this minus sign, so that is minus infinity, correct? So e power infinity is infinity, but e power minus infinity is 0, correct? So 1 by 1 plus 0, that is 1 by 1, which is nothing but 1. Okay, so got the point. In the first case, it will be e power infinity, infinity. So 1 by infinity, 0. In the second case, e power minus any number by 0, that is e power minus infinity is nothing but 0. So 1 by 1 plus 0, 1 by 1, that is nothing but 1. Okay, so these are the two extreme cases, right? If E is less than EF, the probability will be 1. So what is the meaning of the 1 probability? Means it will be definitely be filled, correct? So that is the next point. All energy levels with energies less than EF will be filled. Correct? That's the condition, no? Okay, so if E is less than EF, that power terms numerator will be negative, hence it becomes 1 finally. Correct? So the all energy levels with energies less than EF will be filled. This is the meaning. Okay, so these are the two cases in Fermi-Dirac function. Considering the Fermi energy level, if E is greater than EF, then the probability will be 0. There will be no filled energy levels above this Fermi energy level. And if E is less than EF, then the probability will be 1 that all the energy levels less than the Fermi energy level will be definitely be filled. Okay, so these are the two important cases. Keep the temperature also in mind at 0 degree Kelvin. That is at absolute temperature. Okay. And coming to the three types of semiconductors, that is intrinsic semiconductor and the extrinsic. In extrinsic, there are two types, no? N-type semiconductor and P-type semiconductor. Okay, so these are the formulas. EF equal to, for an intrinsic semiconductor, EF is nothing but the average of the two energy levels. Correct. This is the average formula, no? Okay, so EC plus EV by 2. What is EC actually? EC means, take this diagram, this energy level diagram. We know that the lowest band is the valence band and the highest band is the conduction band, right? So the maximum energy level in the valence band is called as EV, right? Valence band energy level, or we can say that valence band energy maximum, like that also we can say. Okay, and the same way here is the conduction band, right? The conduction band, the lowest energy in the conduction band, lowest energy level in the conduction band is the EC. Okay, this band, this corner. Okay, this edge of the conduction band, the lowest edge of the conduction band is called the EC. That energy level is called EC. EC is nothing but conduction band energy or conduction band minimum. We can say it like that also. This is the valence band maximum and this is the conduction band minimum. Okay. Okay, so we have discussed about EC and EV in the last video also. Okay, so recall that. So the average of the two is nothing but the Fermi energy level in an intrinsic semiconductor. So which means in an intrinsic semiconductor, EF will be exactly in the midway of the forbidden energy gap. This is the forbidden energy gap. You remember yesterday I have discussed EG. Right, this is the forbidden energy gap. An electron has to take that energy or above that energy to jump from the valence band to the conduction band. to become a free electron, right? So that gap is called as forbidden energy gap, EG. And in an intrinsic semiconductor, the Fermi level has to lie midway between the valence band and the conduction band. Got the point? Okay, so next, in an N-type semiconductor, the Fermi level, that formula will be like this: EF equal to EC minus KT into ln NC by ND. Okay, and in P-type semiconductor, the same formula, but in the center there will be plus and KT ln. Here we know NC, and here we have NV, and here ND, and here NA. Okay, what is NC, NA, NV? Okay, NC, ND, NA. So these notations we have seen in this slide particularly. Okay, so this is new parameter. Okay, we have seen about EF. Okay, I have discussed about EC and EV also. What is this NC? What is this NV? And what is this NA and ND? Okay, ND. And what is this NG? I'll say this ND and NA now, and NC and NV in the next slides. Okay, that's some important topics. Okay, ND is nothing but I have discussed today. ND is nothing but the number of donor atoms. Okay, since this is an N-type semiconductor, obviously ND will be appearing in this formula, right? Okay, and Na means number of acceptor atoms. Since this is a P-type semiconductor, we are putting Na in the denominator. Okay, so we can differentiate the two formulas, correct? So here in an N-type semiconductor, we have Nd, and in P-type semiconductor, we have Na. Okay, and coming to Nc and Nv, I will discuss in the further slides. Okay, and then K means Boltzmann constant, and T is the absolute temperature. Okay, so only difference is this minus. Here it is plus, and the formula Nc by Nd, here Nv by Na. Okay, so these are the three important formulas for Fermi level in the three types of semiconductors. Okay, so coming to this energy level diagrams, this is a very important set of diagrams. Kindly have a note on it. So for an intrinsic semiconductor, the Fermi energy level. So look at the location of the Fermi energy level. It lies exactly in the midway. Correct? Exactly in the midway between the conduction band and valence band. Okay. And coming to N-type semiconductor. Okay. These two are extrinsic semiconductors, right? So in an N-type semiconductor, the Fermi energy level lies just above the midway, correct? Just above the midway, or in other words, you can say that it lies below the conduction band. It lies below the conduction band. In the same way, yesterday we have seen about the donor energy level also. In N-type semiconductor, the donor energy level lies below the conduction band, just below the conduction band, right? In the same manner, the Fermi energy level also lies just below the conduction band. Okay, and coming to P-type semiconductor, the Fermi energy level lies below the midway of the forbidden energy gap. In other words, you can say that the Fermi energy level lies just above the valence band. The same way, yesterday we have seen about the acceptor energy level in a P-type semiconductor also. Okay, so we can just compare yesterday's video and today's video also. The same set of understanding only. Okay, you got the point, right? That is donor energy level. Here the same location, Fermi energy level, but just below the donor energy level only actually. Okay, and also in P-type semiconductor, there will be acceptor energy level here, and just above we can see the Fermi energy level in a P-type semiconductor. Okay, so just I'm concluding this. In an intrinsic semiconductor, Fermi energy level lies midway between the conduction band and valence band. In N-type semiconductor, it lies above the midway. Okay, or we can say that it lies below the conduction band also. And in P-type semiconductor, the Fermi energy level lies above the valence band or below the midway of the forbidden energy gap. Okay, we can either view this point in two different manners. Okay, because they'll be given the objective questions in two different ways also. That's a possibility. Okay, so keep that points in mind. And as I have said earlier, we need to know about NC and NV. Okay, so NC is nothing but effective density of states of electrons in conduction band. So conduction band, so that it is notated as NC. Okay, so usually N refers to the number of electrons or number of holes like that, or density. Density means how many charge carriers are concentrated in a particular area. That is nothing but density, right? So NC refers to the effective density of states of electrons in conduction band. And also NV refers to the effective density of states of holes in valence band. Okay, so C refers to conduction band, that and also charge carriers electrons only, and V refers to valence band and also holes. Okay, keep this point in mind. Learn this formula also. This formula is an important formula. Okay, but not widely asked, but that's an important formula. Directly they may be asked, but not widely used for problems and all. But direct questions we can expect from this topic. Okay, NC. NC is nothing but 2 into 2 pi mn kt by h square, the whole power 3 by 2. Okay, where this mn means, this mn is nothing but, okay, mn. M refers to mass, right? N refers to electrons. That's it. Okay, so M means mn. Mn means mass of, effective mass of electrons. And here, instead of this Mn, we are writing as MP. The rest of the formula terms are the same. Okay, you can check, cross check. Okay, so MP means mass of holes. MP means mass of holes. Okay, K refers to Boltzmann constant. Recall the value, 1.38 into 10 power minus 23 joule per Kelvin. And T is the absolute temperature, and H means Planck's constant. Okay, H means Planck's constant. Okay, because that electron has to absorb some energy, no? That energy, that is E equal to H nu. Correct? That H is nothing but Planck's constant. Planck's constant value, that also you might be learnt in the previous chapters. Okay, 6.626 into 10 power minus 34 joule per second. We have learnt a lot of constant values. Okay, am I right? Because Boltzmann constant K, Planck's constant H, and also E. E means the charge of the electron, right? Or a hole, 1.602 into 10 power minus 19 coulomb. Also, I need to mention this M also. M means the mass of the electron or mass of the hole, right? That value is 9.1 into 10 power minus 31 kilogram. That also keep that in mind. Okay, so this entire term will be a constant actually. Okay, so but the number of electrons and holes might vary, so the number also might vary. Okay, so this is the formula for effective density of holes and electrons in valence band and conduction band. Okay, so keep this formula in mind. This might be asked directly, not often in problems. Okay, so இந்த வீடியோ கண்டிப்பாக உங்களுக்கு யூஸ்ஃபுல்லாக இருந்திருக்கும்னு நினைக்கிறேன். இந்த வீடியோவில் ஏகப்பட்ட கான்செப்ட்ஸ் நம்ம பார்த்துருப்போம். மெயினாக மாஸ் ஆக்ஷன்லானா என்ன, இன்ட்ரின்சிக் கேரியர் கான்சன்ட்ரேஷன் என்ன, ஒரு செமிகண்டக்டரோட கண்டக்டிவிட்டி எப்படி கால்குலேட் பண்ணுறது, அதே நேரம் இன்ட்ரின்சிக் செமிகண்டக்டராக இருந்ததுன்னா எப்படி கண்டக்டிவிட்டி வேரி ஆகும். அதே மாதிரி இந்த கான்செப்டும் J equal to sigma into E, இது ஒரு முக்கியமான கரண்ட் டென்சிட்டி ஃபார்முலா. கண்டக்டிவிட்டியும் எலக்ட்ரிக் ஃபீல்டும் கொடுத்துட்டு டைரக்டா கரண்ட் டென்சிட்டி கேட்பாங்க. இது பார்த்தோம். நிறைய கான்ஸ்டன்ட் வேல்யூ நோட் பண்ணிக்கிட்டோம். அதெல்லாமே ஃபியூச்சர்ல நிறைய இடத்துல உங்களுக்கு யூஸ் ஆகும். ஃபெர்மி டிராக் ஃபங்க்ஷன் என்னங்கிறது டிஸ்கஸ் பண்ணோம். ஃபெர்மி எனர்ஜி லெவல்ல என்னங்கிறது டீட்டெயில டிஸ்கஸ் பண்ணோம். அதுல போல்ஸ்மேன் கான்ஸ்டன்ட் பத்தி பார்த்தோம். ரெண்டு டிஃபரெண்ட் கேசஸ் பார்த்தோம் வித் எனர்ஜி லெவல் டயக்ராம்ஸ் அண்ட் ஃபார்முலே, ரைட்? ஸோ 3 டைப் ஆஃப் செமிகண்டக்டருக்கும் டிஃபரெண்ட் ஃபார்முலே இருக்கு. அதுல ஃபெர்மி எனர்ஜி லெவல் எந்தெந்த இடத்துல லொக்கேட் ஆயிருக்குங்கிறதும் நம்ம பார்த்தோம். டிஃபரெண்ட் நோட்டேஷன்ஸோட மீனிங்கும் நான் எக்ஸ்பிளைன் பண்ணேன். NCNV என்ன வித் ஃபார்முலையும் நம்ம பார்த்தோம். இதுல பிளாங்க்ஸ் கான்ஸ்டன்ட் என்னங்கிறதையும் மாஸ் ஆஃப் தி எலக்ட்ரானோட வேல்யூ என்னங்கிறதையும் நம்ம பார்த்தோம். ஓகேவா? ஸோ இது ரிலேட்டடா நான் ஒரு அப்ஜெக்டிவ் கொஸ்டின், ஒரு MCQ மாதிரி ஒரு அப்ஜெக்டிவ் கொஸ்டின் கீழே கமெண்ட்ல பின் பண்றேன். ஸோ அந்த கொஸ்டின்கான ஆன்சர் என்னங்கிறதையும் நீங்க சொல்லுங்க. இதுல இன்னொரு கொஸ்டினும் நான் கேட்டிருந்தேன் வீடியோல, இன்ட்ரின்சிக் கேரியர் கான்சன்ட்ரேஷன் எண்ணெயோட வேல்யூ என்னங்கிறதையும் கேட்டிருந்தேன். ஸோ அதுக்கான ஆன்சர் என்னங்கிறது தெரிஞ்சதுன்னா மறக்காம கமெண்ட்ல சொல்லுங்க. ஓகேவா? ஸோ இந்த வீடியோ உங்களுக்கு யூஸ்ஃபுல்லா இருந்திருக்கும்னு நினைக்கிறேன். யூஸ்ஃபுல்லா இருந்ததுன்னா மறக்காம இந்த வீடியோக்கு ஒரு லைக் கொடுங்க. அந்த அடுத்தடுத்த வீடியோஸ் உங்களுக்கு ரொம்ப ரொம்ப யூஸ்ஃபுல்லான வீடியோஸ்லாம் அடுத்தடுத்து வந்துட்டு இருக்கும். கண்டிப்பா சப்போர்ட் பண்ணுங்க. நம்ம சேனலை சப்ஸ்கிரைப் பண்ணலன்னா சப்ஸ்கிரைப் பண்ணிக்கோங்க. உங்க ஃப்ரெண்ட்ஸ்க்கும் ஷேர் பண்ணுங்க. நெக்ஸ்ட் இன்ஃபர்மேட்டிவான வீடியோல மீட் பண்ணலாம். அது வரைக்கும் தேங்க்யூ.